Welcome, future navigators. Today, we're diving deep into one of the most classic and crucial skills a mariner can possess, finding your position on the open ocean using nothing but the stars. This is celestial navigation, and we're about to tackle a 3-star fix. Imagine this. You're in the middle of the Atlantic, your GPS has failed, and all you have are your wits, a sextant, and the celestial bodies above. This isn't just a classroom exercise, it's a lifeline. Our scenario places us on a vessel in the mid-Atlantic on October 18, 2011. We're steaming along at 10 knots on a course of 230 degrees. As the sun sets, the officer of the watch gets ready to work some magic. The goal is to plot 3 lines of position from 3 different stars and advance them to a common time to get a precise fix of our location. Sounds complex. It is, but we're going to break it down step by step. Let's get our tools ready. We'll need a nautical almanac for 2011, a scientific calculator, triangles, a compass divider, and a plotting sheet. The first star Auru sights is the brilliant Canopus. The time on the chronometer is 20 hours 45 minutes and 0 seconds UTC. The sextant shows an altitude of 67 degrees 46.0 minutes. This is our sextant altitude, or H's. We'll also note our assumed position for this site. Remember, every piece of data is critical. We also have an index error on our sextant of 1.2 minutes off the arc, and our height of eye is 20 meters. These are corrections we'll apply later to get from our observed altitude to the true altitude. Just a few minutes later, at 20 hours 48 minutes and 0 seconds UTC, we take our second sight. This time, it's the star Nunki. The sextant altitude is 29 degrees 105 minutes. We record this along with the new time and our slightly updated assumed position. Why do we need multiple stars? Because one star only gives you a single line of position, or LOP. It tells you that you are somewhere on a very large circle on the Earth's surface. A second LOP will intersect that first one at 2 points, narrowing it down. But it's the third star that gives us the coveted fix. Our third and final celestial partner for the evening is Alkaid, sighted at 20 hours 50 minutes and 30 seconds UTC. The sextant altitude is 26 degrees 38.1 minutes. Now we have our 3 raw observations, but these sights were taken at different times and our ship is moving. We can't just plot them as they are. This is where the real work of a navigator begins. We need to advance the first 2 lines of position to the time of the third sight. This creates a running fix. So, what's the process from here? For each star, we have a journey of calculation ahead of us. First, we need to correct our sextant altitude. We'll apply the index error and then the dip correction for our height of eye. This gives us the apparent altitude. Then, we use the nautical almanac to find the main correction for the star's altitude, which accounts for atmospheric refraction. We also have some additional environmental data, a temperature of 9 degrees Celsius and pressure of 10-12 millibars, which will require a small additional correction. Applying all of these gives us our observed altitude, or HO. This is what we actually saw. Next comes the theoretical part. For each sight's time and assumed position, we will calculate what the altitude asterisk should asterisk have been. This is the computed altitude, or HC. This involves diving into the nautical almanac to find the Greenwich hour angle Ya varies, adding the sidereal hour angle SHO of our specific star, and applying our assumed longitude to get the local hour angle LHA. Using the LHA, our assumed latitude, and the star's declination also from the almanac, we use a spherical trigonometry formula to solve for HC and the azimuth, which is the star's true bearing from our position. Now for the moment of truth, comparing what we saw with what we calculated. The difference between our observed altitude HO and our computed altitude HC is called the intercept. It's measured in nautical miles. If Ho is greater than HC, our true position is towards the star from our assumed position along the azimuth line. If Ho is less than HC, we are away from the star. This intercept is what lets us draw our line of position on the plotting sheet. Each lop is drawn perpendicular to the star's azimuth line at the distance of the intercept. We'll do this for Canopus, then for Nunki, and finally for Alkaid. But remember, the ship is moving. Let's say we decide to advance everything to 20 hours, 50 minutes, and 30 seconds, the time of our Alkaid sight. The Canopus sight was taken 5.5 minutes earlier. At 10 knots, we traveled about 0.9 nautical miles on a course of 230 degrees. So, we must move the entire Canopus lop by that distance and direction. Similarly, the Nunki sight was 2.5 minutes earlier, so we'll advance its lop as well. Once we've plotted the advanced lop for Canopus, the advanced lop for Nunki, and the LOP for Alkaid all on our plotting sheet, we should see them intersect. In a perfect world, they would all cross at a single point. In reality, due to small errors in observation or calculation, they'll form a small triangle, often called a cocked hat. The center of this triangle is our fix. This is our position on the vast expanse of the Atlantic Ocean, determined by the ancient art of celestial navigation. For students undertaking this exercise, the goal is to get a final position that's within 2 nautical miles of the correct answer. You'll be graded on each step of the process, from correctly noting the times and positions to calculating the GOS, LHAs, altitudes, azimuths, and finally, the intercepts. Every single step matters. You'll solve for the calculated altitude, true altitude, azimuth, and intercept for all 3 stars. Then you'll bring it all together on the plotting sheet to find that final fix. It's a challenging but incredibly rewarding process. This exercise isn't just about passing a test. It's about building the fundamental competence of a skilled mariner. It's about knowing you have the ability to find your way no matter what technology fails. It connects you to a tradition of seafarers stretching back centuries who look to the same stars to guide them home. It's a beautiful blend of science, art, and meticulous practice. So, grab your almanac and calculator and let's navigate by the stars. Thanks for joining me on this celestial journey. Be sure to like and subscribe for more deep dives into the world of navigation. Stay safe out there.